Tonight we are going to talk about the Sun. Not the Sun as an abstract object of study, not as statistics and temperatures and distances in kilometers, but the Sun as what it really is, the reason everything you know exists, the reason there is liquid water on Earth, the reason there is life, the reason there is day and night, spring and winter, a blue sky and a sunrise. The Sun is the source of almost all the energy flowing through the ecosystems of this planet, and it has been shining with extraordinary stability for 4.6 billion years. And one day it will go out. Not suddenly. Not like a candle being extinguished. The process will be long, gradual, and in its final phases, from the perspective of anyone who might be watching, extraordinarily beautiful. But the final result will be the same. Where there is now a star warming and lighting 8 planets, there will be a cold and dark object drifting silently through space, the cooled corpse of what was once the center of our solar system. That story, the story of the birth, life, and death of the Sun, is what we are going to explore tonight. Not with fear, because what we are about to describe will happen on timescales so incomprehensibly long that no anxiety makes sense. But with the curiosity and wonder that a story of this magnitude deserves. A story that began 4.6 billion years ago in a cloud of interstellar gas and dust, and that will end, in its final consequences, billions of years from now in the cold darkness of the future universe. The Sun above your head right now is approximately 4.6 billion years old. It is in the middle of its life. It is a mature, stable star in the phase astronomers call the main sequence, which is the longest and most tranquil phase in the life of any star. In that phase, the Sun burns hydrogen in its core through nuclear fusion, converting 4 million tons of matter into pure energy every second, and that energy flows outward through the Sun's layers and eventually escapes as the light and heat that reach the Earth 8 minutes later. 4 million tons per second. To put that in perspective, that is roughly equivalent to detonating 42 billion hydrogen bombs every second, continuously, for 4.6 billion years. And the Sun will keep doing this for approximately another 5 billion years before its hydrogen fuel in the core is exhausted and things begin to change. 5 billion years is a time the mind cannot truly represent. If we compressed the Sun's past history into a year, 5 billion more years would be another complete year. All of human civilization, every bit of history from the first cities 5,000 years ago to today, would occupy less than a second on that calendar. The time the Sun has left before beginning its transformation is simply unimaginable in human terms. But stars do not think in human terms. The Sun will keep shining with the same tranquil indifference during that incomprehensible time, and then it will begin to change, and that change is what we are going to follow tonight. To understand how the Sun will die, you first need to understand how it lives. What is happening in its interior right now, what forces are in balance, and what will happen when that balance begins to break down. The Sun is fundamentally a ball of plasma, a gas so hot that electrons have separated from atomic nuclei, held together by its own gravity. In the solar core, where the temperature exceeds 15 million degrees Celsius and the pressure is 250 billion times Earth's atmospheric pressure, hydrogen nuclei move so fast and are so compressed that they collide with sufficient frequency for nuclear fusion to occur continuously. Nuclear fusion is the process by which 4 hydrogen nuclei combine to form a helium nucleus, releasing in the process a small amount of energy as gamma-ray photons. The word small is relative, because the energy released in each individual reaction is very small in human terms, but it occurs in astronomical quantities. Approximately 900 quadrillion fusion reactions occur in the solar core per second. The energy produced in the core does not reach the surface immediately. A photon generated in the solar core takes on average between 100,000 and a million years to make its way out, because the solar interior is so dense that photons are continuously absorbed and re-emitted in different directions, advancing in a random walk on their way to the surface. The sunlight illuminating you today may have been generated in the core at a time when the first anatomically modern humans were beginning to disperse across Africa. This fusion process produces an outward pressure, the radiation pressure and the thermal pressure of the hot gas, that exactly counteracts the gravitational pressure trying to collapse the sun toward its center. It is an exquisite balance that has kept the sun stable for billions of years and will continue for billions more. When astronomers say the sun is on the main sequence, they are describing precisely this state of balance between inward gravity and outward pressure. But the balance is not static. As hydrogen in the core is converted to helium, the core's composition gradually changes. Helium, being heavier, accumulates in the center while hydrogen is consumed. This has effects that occur very slowly but are inevitable and that will eventually break the current balance. The sun today is approximately 45% more luminous than it was when it formed 4.6 billion years ago. That greater luminosity is a consequence of gradual changes in the core composition. And that same process will continue in the future, making the sun progressively brighter as the eons pass. Within approximately 1 billion years, the sun will be bright enough to have warmed the Earth beyond the point where oceans can remain stably liquid, and life on Earth's surface will begin facing increasingly extreme conditions. That gradual warming process is in many ways more immediately relevant to life on Earth than the sun's final death, which is still 5 billion years away. But it is also a signal of the more dramatic transformations to come, when the core's hydrogen is completely exhausted and the sun enters the final phases of its life. The critical moment in the sun's life will arrive when the core runs out of hydrogen to burn. At that moment, approximately 5 billion years from now, hydrogen fusion in the core will stop. Without the radiation pressure counteracting gravity, the core will begin to contract under its own weight. That contraction of the core is the trigger for everything that follows. And its effects are, paradoxically, the opposite of what might intuitively be expected. When the core contracts, the temperature in the surrounding layers increases. Those layers still contain unburned hydrogen, and when the temperature rises enough, fusion begins to occur in those outer layers instead of in the core. The sun enters what astronomers call the hydrogen shell-burning phase. Shell burning produces more energy than the previous central fusion, not less. That may seem counterintuitive, but it is a consequence of the geometry and physics of the situation. The greater energy production generates greater outward pressure, and the result is that the sun's outer layers begin to expand. The sun starts to grow larger. During the first millions of years of this phase, the change is gradual and almost imperceptible. But as the core continues to contract and heat up, and as the fusion shell produces ever more energy, the expansion accelerates. The sun begins to swell outward in a way that in cosmic timescales is quite rapid. At the same time as the sun expands, its surface cools. This may also seem paradoxical. More energy produced but a cooler surface. The reason is that the same amount of energy has to be distributed over a much larger surface. When the surface cools, it changes color, from yellow toward orange and then toward red. And when astronomers see an enormous red-colored star, they call it a red giant. The sun will become a red giant. That is the inevitable destiny of any star of similar mass to ours when it exhausts its core hydrogen. And the scale of what will happen when that occurs is difficult to exaggerate. At its maximum as a red giant, the sun will expand to approximately 200 times its current size. The sun's current radius is approximately 700,000 kilometers. As a red giant, that radius could reach 140 million kilometers or more. For comparison, the Earth's current distance from the Sun is 150 million kilometers. This means the expanded Sun could fill practically all of Earth's orbit, or completely swallow it depending on which estimates are used. Mercury and Venus will undoubtedly disappear inside the expanded Sun. Earth might be swallowed as well, though some models suggest it might just barely sit at the edge of the expanded solar atmosphere. In any case, by that point Earth will have been a completely uninhabitable world for billions of years, not because of the Sun's expansion but because of the gradual warming mentioned earlier. The question of whether Earth is physically swallowed is in some sense irrelevant to the story of life, which will have ended much earlier. The Sun's red giant phase will last approximately 1 billion years, though with variations in the intensity and scale of what happens. It is not a linear and uniform process. It is a series of distinct phases, each with its own physics, its own duration, and its own consequences for the solar system. During the red giant phase, the outer planets of the solar system will experience something extraordinary. Their icy moons, worlds that today are balls of ice in the distant cold of the outer solar system, will begin to receive enough heat for their surface and subsurface ice to melt. Europa, Jupiter's moon that is believed today to have a liquid ocean beneath its ice crust, could see that ocean expand to the surface. Enceladus, Saturn's moon with its water vapor geysers, could become a world with surface oceans. Titan, Saturn's moon with its dense atmosphere and hydrocarbon lakes, could experience transformations that no current model can predict with certainty. If at that future time some form of life exists on any of those worlds, and the possibility is not unreasonable given the time that will have elapsed and the conditions that already exist in some of them today, that life will face a radical change in its environment. Temperatures will rise over tens of millions of years, producing conditions that by those icy world standards would be equivalent to a cosmic spring. And then the temperature will keep rising, and that spring would become summer and then unbearable heat, and eventually the same sterilization that will have befallen Earth much earlier. But at the heart of the expanded Sun, something more is happening in the meantime. The core has continued contracting and heating until it reaches temperatures of approximately 100 million degrees Celsius. At that moment, something is triggered that astronomers call the helium flash. The helium flash is one of the most violent events in the life of a sun-like star, though paradoxically it is completely invisible from the outside. It occurs when the accumulated helium core reaches sufficient temperature for helium to begin fusing into carbon and oxygen. Helium fusion is very different from hydrogen fusion in its dynamics, because the accumulated helium in the core is in a special state called electron degeneracy, in which pressure does not depend on temperature in the usual way. When helium fusion begins in a degenerate core, the released energy does not produce the expansion that would normally stop the reaction. Instead, it produces more temperature, which produces more fusion, which produces more temperature, in a feedback loop that runs away for a very brief period. In a fraction of a second, the solar core releases more energy than all that the Sun has produced throughout its entire life. But that energy is absorbed by the Sun's surrounding layers, and no signal of this interior cataclysm reaches the surface. For any external observer, the Sun simply continues shining as always. After the helium flash, the core readjusts. The electron degeneracy breaks, and the core expands until it finds a new stable equilibrium in which helium fuses in a controlled manner into carbon and oxygen. The Sun enters what is called the horizontal branch, a new phase of relative stability in which it can last another 100 million years. The 100 million years of the horizontal branch phase are, in cosmic terms, a brief but relatively peaceful period. The Sun burns helium in its core, producing carbon and oxygen, and hydrogen fusion continues in the shell surrounding the core. The solar system has been dramatically reorganized compared to what it was. The inner planets have disappeared or been devastated. The outer planets have received an unprecedented dose of heat in their history, but there is a temporary stability that will last as long as the core's helium holds out. But helium runs out too, faster than hydrogen, because helium fusion produces more energy per unit time and consumes fuel at a greater rate. When the core's helium runs out, the Sun repeats the cycle that occurred when the central hydrogen ran out. The core contracts, temperature rises, and fusion continues in progressively outer layers. But this time the result is more dramatic. The Sun enters what is called the asymptotic giant branch, and in this phase it becomes unstable in a way it did not have in the first red giant phase. The simultaneous burning of hydrogen and helium in different layers produces thermal pulses, episodes of unusually intense fusion that occur approximately every 100,000 years and that cause expansions and contractions of the Sun that have no equivalent in any earlier phase of its life. During each thermal pulse, the Sun may briefly expand to sizes that exceed even its maximum as a red giant, and in those expansions the Sun's outer layers become so tenuous and so weakly bound gravitationally that the solar wind, which had already intensified enormously in earlier phases, drags them into space. The Sun begins to lose mass significantly. This mass loss process is fundamental to what comes next. A Sun that retained all its mass would eventually collapse in a very different way from what will actually happen. But asymptotic giant branch stars lose mass at a rate that on timescales of millions of years is enormous. The Sun could end up losing between 40 and 50% of its total mass during this phase, ejecting entire layers of gas into space that in the cold interstellar medium cool and form structures of a beauty that no terrestrial process can equal. Those structures are planetary nebulae. The name is misleading because they have nothing to do with planets. It was a term coined by early astronomers who observed them because their circular appearance reminded them of the disks of planets as seen through telescopes of that era. In reality, they are the outer layers expelled from Sun-like stars in their final active moments, illuminated by the ultraviolet radiation from the hot, bare core that remains at the center. Planetary nebulae are some of the most beautiful objects in the observable universe. They have shapes ranging from perfect rings to symmetrical butterflies, from concentric bubbles to columns of gas like cathedral pillars. Their colors are the result of different elements ionized by ultraviolet radiation. Ionized hydrogen produces the characteristic red of many nebulae, doubly ionized oxygen produces green and blue, ionized nitrogen produces orange tones. They are cosmic works of art produced by the most basic physics of how atoms emit light when excited. The nebula the Sun will produce when its time comes will last approximately 10,000 years before the gas disperses too much and becomes invisible. 10,000 years is a blink in cosmic timescale, but enough for during that period the solar system to shine with a light that no earlier phase of the Sun's life has produced. At the center of the planetary nebula, when the outer layers have been expelled, what was the Sun's core is exposed. It is an object approximately the size of the Earth, incredibly hot, incredibly dense, shining with intense ultraviolet light. It is what astronomers call a white dwarf. The white dwarf that will remain from the Sun has no fuel to burn. There is no nuclear fusion in its interior. The pressure that holds it against gravitational collapse is not the pressure of hot gas or radiation pressure, but something fundamentally different and much more exotic: the pressure of electron degeneracy. Electron degeneracy pressure is a consequence of the Pauli exclusion principle of quantum mechanics, which says that two electrons cannot occupy the same quantum state simultaneously. When matter is compressed to extreme densities, electrons are forced to occupy higher energy states simply because the lower energy states are already full. That quantum resistance to the stacking of electrons produces a pressure that does not depend on temperature, that is not reduced if the object cools, and that can hold the white dwarf against collapse indefinitely. A white dwarf the size of the Earth will contain approximately half the Sun's current mass, about 600,000 trillion cubic kilometers of matter compressed into a sphere of barely 13,000 kilometers in diameter. 1 cubic centimeter of its material would weigh approximately 1 ton, 1,000,000 times more than water. It is an object of a density that no material on Earth can approximate. The temperature of the newly formed white dwarf will be tens of thousands of degrees Celsius, and it will shine with extraordinary intensity in blue-white light. But it has no internal energy source. It produces no new energy. It only radiates the residual heat accumulated throughout its history as an active star. And that heat, with no replenishment source, will gradually be lost to space, cooling over billions of years. A young white dwarf is bright and hot. A white dwarf several billion years old is less bright and cooler. A very old white dwarf is dim and orange. And a sufficiently ancient white dwarf would be invisible, a dark and cold object drifting through space emitting no visible light. Astronomers call this hypothetical object a black dwarf. We say hypothetical because as far as we know, no black dwarf exists in the current universe. The universe has not had sufficient time for any white dwarf to cool completely to that state. The oldest known white dwarfs still have surface temperatures of several thousand degrees and remain faintly visible. Cooling to total darkness would require more time than the universe has existed so far. The white dwarf that will remain from the Sun will cool for trillions of years. There is no process to heat it, no fuel that can ignite, no gravitational collapse that can produce additional heat because electron degeneracy pressure prevents it. It will simply cool, slowly, incrementally, losing heat to space for a time that makes the current history of the universe seem like an instant. The story of the solar system after the Sun's death does not end with the white dwarf. There are consequences for the surviving planets, for the orbits of remaining objects, for the structure of the solar system as a whole that deserve to be explored. When the Sun loses mass during the asymptotic giant branch phase, the orbits of all planets will change. The Sun's gravity at that point will be less because its mass will have decreased. Orbits, which are the result of the balance between planets' velocities and the Sun's gravitational attraction, will expand. The outer planets, Jupiter, Saturn, Uranus, and Neptune, will move out to larger orbits in response to the reduced solar mass. Jupiter, which currently orbits at 5 astronomical units from the Sun, could find itself orbiting at 7 or 8 astronomical units when the mass loss process has ended. Neptune, currently at 30 astronomical units, could shift to 40 or more. The solar system remaining after the red giant phase and the expulsion of the planetary nebula will be geometrically different from the one that exists today. The outer planets will have experienced several billion years of warming during the red giant phases. Their atmospheres will have been transformed. Their moons will have undergone dramatic changes. Depending on how long they remain in the expanded habitable zone that the red giant sun will create around it, some of those worlds could have had liquids on their surfaces for geologically significant periods. When the Sun finally becomes a white dwarf and the planetary nebula disperses, the surviving outer planets will orbit that compact object in broader trajectories than current ones. The solar system will have become much more tenuous and colder. The white dwarf will emit far less light and heat than the current Sun, and the surviving planets will receive a minimal fraction of the energy they receive today. In this configuration, the outer solar system planets could continue orbiting the white dwarf for billions of years, or even longer. There is no process that quickly eliminates them. Mutual gravitational perturbations between planets could eventually destabilize some orbits, sending one planet on a collision course with the white dwarf or expelling it completely from the solar system. But those processes are slow and stochastic. On much longer timescales, even the white dwarf could eventually capture one of its planets through gravitational tides or could gradually lose all of them to galactic perturbations. Nearby stars, over the course of billions of years of the white dwarf's life, will exert small but cumulative gravitational perturbations on the solar system. On timescales of trillions of years, the solar system could be completely dismantled by these distant interactions. And the white dwarf itself will continue its slow cooling. It will go from white to yellow to orange to red to invisible. On timescales measured in quadrillions of years, it will approach the state of black dwarf. Not completely cold, because the cooling of such a massive object never ends exactly, but so cold that no instrument of any civilization existing at that time could distinguish it from the surrounding empty space. There is something happening in the Sun's neighborhood right now that is relevant to everything we have described. A signal that astronomers have been receiving for decades and that speaks directly to the processes we have explored, though from different stars than our own. Throughout the observable universe there are billions of stars in various phases of their evolution. Young stars that have just ignited in gas and dust clouds. Mature stars on the main sequence, like the Sun aging stars in various phases of the giant branch. White dwarfs of different ages and temperatures. And occasionally, during violent mass loss events or interactions between stars, objects that briefly shine with an intensity that can exceed an entire galaxy. The planetary nebulae we see today in the universe are stars that have recently died in cosmic terms. Some of the most famous are objects of extraordinary beauty. The Cat's Eye Nebula, the Ring Nebula, the Butterfly Nebula, each is the light-wrapped corpse of a star that was like the Sun a few thousands or tens of thousands of years ago. By observing them, we can see directly what the solar system will look like when its turn comes. The Ring Nebula, in the constellation Lyra, is one of the most studied and most photographed of all. It is approximately 2,300 light-years from us, and Hubble Space Telescope images show a complexity of structure that defies any simple description. There is a bright central ring formed by ionized oxygen gas that produces the characteristic blue-green color. Surrounding that ring are layers of ionized hydrogen and nitrogen that produce red and orange tones. And at the center, barely visible as a blue point of light, is the white dwarf that was the nucleus of the star that died. When astronomers of the future, if there are any, look toward where the Sun is today in about 8 to 10 billion years, they will see something similar. A nebula that will shine for about 10,000 years before dispersing. And at the center of that nebula, the white dwarf that will be the only remnant of the Sun we know. Observatories existing today on Earth and in space have cataloged thousands of planetary nebulae in our galaxy. Each one is the end of a story like the Sun's, at a different scale depending on the mass of the original star. Stars more massive than the Sun go through more dramatic phases and die in more violent ways, producing supernovae instead of planetary nebulae. Less massive stars die in quieter ways but still produce similar nebulae. The Sun, with its intermediate mass, will produce a nebula of medium size and complexity, notable but not extreme in the context of everything that exists in the galaxy. There is something profound in observing these nebulae. They are not just aesthetic objects, though they are of extraordinary beauty. They are reminders that stellar death is not destruction but transformation. The gas a star expels when it dies does not disappear. It disperses through interstellar space, cools, mixes with the gas already there, and eventually, over millions of years, can collapse again under gravity to form new stars and new planetary systems. The death of a star is the seed of the next generation. There is a question that arises naturally when exploring the Sun's destiny, and that is what will happen to Earth long before the Sun reaches its red giant phase. Because Earth does not have to wait to be swallowed by the expanded Sun to face conditions that make life as we know it impossible. The Sun gradually increases its luminosity as helium accumulates in its core and hydrogen fusion occurs slightly more efficiently. This is a trend that has existed throughout the Sun's history and will continue. 4 billion years ago, the Sun was approximately 70% of its current luminosity. Today it is 100%. Within 1 billion years, it will be approximately 10% brighter. 10% more solar light and heat may seem modest. But Earth is a climate system extraordinarily sensitive to changes in received energy. That increase in solar luminosity, distributed over 1 billion years, will produce a gradual warming of the planet's average temperature. Climate feedbacks, including increased ocean evaporation and the resulting greenhouse effect increase, will amplify that warming. The most detailed climate models suggest that in approximately 1 billion years, Earth's average temperature will be high enough that the moist greenhouse effect becomes unstable. At that point, ocean water will begin to evaporate faster than it can condense in a self-feeding process. More water vapor in the atmosphere produces more greenhouse effect, which produces more temperature, which produces more evaporation. The final result would be the loss of all oceans through the atmosphere in a process scientists call the runaway greenhouse. Earth would become something similar to Venus, a planet with a dense carbon dioxide atmosphere and surface temperatures of hundreds of degrees. Without liquid water, without the water cycle, without the biogeochemical processes that depend on liquid water, life as we know it would be impossible. But before that extreme point, life on Earth will have faced progressive changes over hundreds of millions of years. The temperature increase will affect nutrient circulation in the oceans. It will change precipitation patterns. It will shift habitable zones toward the poles. It will reduce the diversity of ecosystems that can be sustained. Life will not disappear all at once, but will adapt, evolve, retreat before the advance of increasingly extreme conditions, over a time that is geologically enormous, though only a fraction of the Sun's total life. This perspective has something serene about it when contemplated from the appropriate distance. Earth is not permanent. The Sun is not permanent. The solar system is not permanent. Everything that exists has a history that began at some point and will end at another. Life on Earth is a chapter in a longer story, and that chapter will have an ending, as all chapters do, though the ending is a billion or several billion years away depending on what kind of life and what conditions we consider. Awareness of that impermanence need not be depressing. It can be, if inhabited correctly, one of the most liberating perspectives that exist. What exists now? This planet with its oceans and forests and animals and cities and conscious beings wondering about the Sun's fate exists now. And that now has a value that does not depend on its duration. There are other solar systems in our galaxy where what will happen to ours has already occurred. Stars that were like the Sun but are older, that have already gone through the red giant phase, that have already become white dwarfs. And in some of those systems, astronomers have found evidence of what remained. In recent years, telescopes have observed white dwarfs showing in their atmospheres traces of heavy elements such as calcium, magnesium, silicon, and iron. This is significant because white dwarfs have pure hydrogen or helium atmospheres. The extreme gravity of these compact objects causes any heavier element to sink rapidly toward the interior, out of reach of spectrometers. The presence of heavy elements in a white dwarf's atmosphere means those elements arrived there recently, in astronomical timescales. The most likely explanation is that those elements are the remains of planets, asteroids, or comets that were torn apart by the white dwarf's tidal forces when they got too close, and whose fragments are being gradually accreted onto the white dwarf's surface. In other words, astronomers are watching white dwarfs eating the remains of their own planetary systems. Those planetary systems, in their glory days, might have been similar to ours. They may have had habitable planets, oceans, atmospheres, perhaps life. Now they are rock fragments disintegrating in the atmosphere of a compact and cold object. It is a direct reminder of what awaits the solar system in the distant future. But there is also something hopeful in that image, though it may seem paradoxical. The material of those destroyed planets does not disappear. It becomes part of the white dwarf, or remains floating in the system as dust and gas that could eventually aggregate into new structures. In the universe, matter is conserved. The carbon and oxygen and silicon atoms that formed those planets are the same atoms that will form the next planets when the system reorganizes, that will form the next stars when the interstellar gas collapses again. The galaxy has been doing this for 13 billion years. Stars that are born, live, and die. Their remains dispersing into interstellar space. New generation of stars forming from those remains enriched with the elements the previous generation manufactured in their cores. The Sun is a star of at least the third generation, formed from material that has gone through at least 2 previous cycles of stellar life and death. The atoms of your body have been in other suns, in other planets, before arriving here. That cosmic continuity, that perpetual recycling of matter through generations of stars, is perhaps the greatest story that astrophysics can tell. It is not a story of destruction, but of transformation. Not a story of ending, but of continuation through successive forms. The Sun will die, but the matter composing it will not disappear. It will disperse, transform, and eventually, on cosmic timescales, become part of something new. Before closing this journey through the Sun's destiny, there is something more that deserves to be contemplated. Not a scientific fact, but a perspective. A way of relating to everything we have explored tonight that goes beyond data and figures. The Sun has been shining for 4.6 billion years. In that time, it has seen Earth form, has seen the first living organisms appear approximately 3.8 billion years ago, has seen the slow process of evolution that produced cells with nuclei, then multicellular organisms, then plants, then animals, then mammals, then primates, then human beings. It has seen the emergence of consciousness, of language, of abstract thought, of the science that today allows us to understand what will happen to it in the future. Throughout all that time, the Sun has not changed appearance in any appreciable way. It has been, for all the life that has existed on this planet, a constant. A source of light and heat so stable and so permanent that it could be confused with an intrinsic property of the universe rather than the temporary state of an object with its own history and destiny. Contemplating that history and that destiny produces something few intellectual experiences can equal. It produces the perspective of timescale, the understanding that what seems permanent is always temporary, that what seems immutable is always changing, only in timescales that exceed any individual experience. Earth seems solid and immutable beneath our feet, but it has been in continuous motion for 4.6 billion years. The Sun seems eternal in the sky, but has a history and a future as specific as those of any living being. That perspective of timescale does not make us smaller. It places us in a more honest context. We are part of a much longer story than human history, part of a cosmic process that began long before we existed and will continue long after we have disappeared as a species. And in that context, the fact that we exist, that we are conscious, that we can ask these questions and understand these answers, is something truly extraordinary. The Sun will shine tonight, as it has shone every night for 4.6 billion years. Its photons will cross space, reach the Moon and illuminate it, disperse through the solar system, some of them traveling for billions of years before being absorbed by some grain of dust in interstellar space. And you will be here, in the darkness of night, contemplating the fate of the star that made everything you are possible. There is a peculiar calm in that image. The enormity of the time remaining before the Sun begins to change in earnest dissolves any urgency. The Sun will still be shining when you have slept, when you have woken, when you have lived your entire life, when all the people you know and all who will know your descendants for thousands of generations have lived their lives. The continuity of that light is one of the most constant things that exists. The Sun's death will not occur in isolation. It will happen in the context of a galaxy that also has its own history and its own future. The Milky Way, that disk of 400 billion stars that is our cosmic home, is currently on a collision course with another galaxy. The Andromeda Galaxy, the great spiral we see in the night sky as a faint smudge 2.5 million light-years away, is moving toward us at approximately 110 kilometers per second. At that speed, Andromeda and the Milky Way will collide in approximately 4.5 billion years, just as the Sun is in the final stages of its main sequence life and beginning its transformation into a red giant. The collision between the two galaxies is one of the most dramatic events that will occur in the solar system's history, though paradoxically it will not be dangerous in the sense of producing direct physical collisions. Galaxies are composed mainly of empty space. Stars are so small compared to the distances separating them that when two galaxies collide, almost no individual star physically collides with another. What happens instead is that gravitational interactions between the two galaxies distort their structures, produce long arms of stars flung into intergalactic space, and eventually merge the two galaxies into a single elliptical galaxy. This process will last several billion years. During that time, the solar system could be displaced to a different region of the combined galaxy, though it will probably survive intact as a system. The gravitational disturbances the galactic merger will produce are on timescales so long that their effect on an individual solar system would be subtle, though they could alter the Oort cloud, the reservoir of comets at the solar system's periphery, and produce a higher frequency of comet showers into the inner system. The combined resulting galaxy, which astronomers have already informally named Milkomeda, will be an elliptical galaxy without the spiral structure characteristic of its progenitors. Elliptical galaxies generally have less active star formation than spirals because the cold gas needed to form new stars has largely been consumed or heated. Milkomeda will be an older and quieter galaxy than the current Milky Way. The Sun and its residual planetary system, by the time of the galactic merger, will be in the final stages of the Sun's life. The white dwarf remaining from it will exist within this new combined galaxy, slowly drifting in its new orbit around the massive galactic center, gradually cooling over the eons. The Sun does not only send light and heat into the solar system. It continuously emits a stream of charged particles, mainly protons and electrons, traveling outward at speeds between 300 and 800 kilometers per second. This is called the solar wind, and it has consequences for every planet in the solar system. On Earth, the solar wind is deflected by the planet's magnetic field before reaching the surface, creating the magnetosphere that protects us from this rain of energetic particles. When the solar wind interacts with the magnetosphere in polar regions, where the magnetic field is weaker and allows some particles to enter the atmosphere, it produces the northern and southern auroras, those light displays that tint the sky green, red, and blue on nights of high solar activity. The solar wind also produces the heliosphere, a giant bubble of solar material extending far beyond Neptune's orbit. The heliosphere has a radius of approximately 100 astronomical units, meaning it extends 100 times the Earth-Sun distance in all directions. At its boundary is the heliopause, where the solar wind stops and the interstellar wind of outer space takes over. The Voyager 1 probe, launched in 1977, crossed the heliopause in 2012 and became the first human-made object to enter interstellar space. It is still traveling outward at approximately 17 kilometers per second, and right now is more than 23 billion kilometers from Earth. Its radio signal takes more than 22 hours to arrive, traveling at the speed of light. As the Sun evolves toward the red giant phase, the solar wind will intensify enormously. The Sun's mass loss rate during that phase could be millions of times greater than today's. The heliosphere will expand dramatically, and the outer planets of the solar system will be immersed in a stream of solar material that will fundamentally change their atmospheres. The intensified solar wind during the Sun's final phases will also be the mechanism that expels into interstellar space the outer layers that will eventually form the planetary nebula. It is not a violent explosion, but a gradual mass loss process driven by this intensified wind that accumulates the dying star's ejecta into the beautiful structure that telescopes will observe from other parts of the galaxy. The nuclear fusion that keeps the Sun burning is one of the most efficient processes for releasing energy that physics allows. When 4 protons fuse to form a helium-4 nucleus, the mass difference between the 4 protons and the helium nucleus is converted into energy according to Einstein's famous equation. That difference is small, approximately 0.7% of the original mass, but multiplied by the speed of light squared produces an enormous amount of energy. For comparison, The nuclear fission that occurs in Earth's atomic reactors has an energy conversion efficiency of approximately 0.1%. Hydrogen to helium fusion is approximately 7 times more efficient. And the Sun has so much mass, so much hydrogen to fuse, that it can sustain that process for billions of years. Fusion in the solar interior occurs primarily through what is called the proton-proton chain. It is a sequence of reactions in which first 2 protons fuse to form a deuteron, emitting a positron and a neutrino. Then that deuteron fuses with another proton to form a helium-3 nucleus, emitting a gamma photon. And finally 2 helium-3 nuclei fuse to form a helium-4 nucleus and release 2 protons back into the process. Each step of this chain produces neutrinos, particles that almost do not interact with matter and that escape the Sun in a matter of seconds without being absorbed. Solar neutrinos pass through Earth as if it did not exist. At this very moment, as you read this, approximately 65 billion solar neutrinos are passing through every square centimeter of your body per second, without you feeling anything at all. The detection of these solar neutrinos was an extraordinary scientific milestone. The first solar neutrino detection experiments, conducted in deep mines to isolate them from cosmic ray background, detected fewer neutrinos than the standard solar model predicted. For decades, this was known as the solar neutrino problem, generating debates about whether the solar model was incorrect or whether there was something wrong with our understanding of neutrinos. The resolution came when it was discovered that neutrinos have mass and can change from one type to another during their journey from the Sun to Earth, a process called neutrino oscillation. Earlier experiments were only sensitive to one type of neutrino, and solar neutrinos were changing to other types during the journey. When experiments sensitive to all types were designed, the observed number matched the solar model's predictions. The Sun was working exactly as physics predicted. Jupiter deserves a chapter of its own in the solar system story. Not because it is the most dramatic of the planets, but because its role in Earth's history of life has been fundamental, and its future after the Sun's death is one of the most interesting to consider. Jupiter has a mass of approximately 318 Earth masses, and is more massive than all other planets of the solar system combined. That extraordinary mass makes Jupiter the second gravitationally most important object in the solar system after the Sun. Its gravitational field reaches to the confines of the solar system and has shaped the distribution of asteroids, comets, and planets for 4.6 billion years. The asteroid belt between Mars and Jupiter contains billions of objects, but contains far less mass than it would if Jupiter had not been there during the solar system's formation. Jupiter's gravitational resonances have expelled from the belt most of the material that would otherwise have accumulated there, and have kept the belt in a state of perpetual agitation that prevents its objects from aggregating to form a planet. The asteroid belt is, in a sense, the corpse of a planet that could never form because of Jupiter's gravitational interference. That same gravitational interference has historically protected Earth from many large comet and asteroid impacts. When a comet from the Oort cloud enters the inner solar system, it has a significant probability of being captured or deflected by Jupiter's gravity before reaching Earth's orbit. The frequency of massive impacts on Earth would have been much greater without Jupiter. In the future, when the Sun has died and Jupiter is in an expanded orbit around the white dwarf, its role will change. The white dwarf will have approximately half the current Sun's mass, meaning its gravitational pull on Jupiter will be less. Jupiter will move to a wider orbit, perhaps 7 or 8 astronomical units instead of the current 5. In that new configuration, Jupiter will still be the most massive object in the solar system after the white dwarf. Its gravitational interactions with other surviving planets will continue shaping the system. And the Oort cloud, which will have been significantly perturbed during the Sun's mass loss phases, could send a shower of comets into the inner system, which by that time would be dominated by the cold white dwarf. Eventually, on timescales of many billions of years, galactic perturbations could destabilize Jupiter's orbit. The gravitational field of stars passing near the solar system, though none will pass close enough to produce dramatic effects on human timescales, accumulates effects over cosmic timescales. Jupiter could be expelled from the solar system in a chance gravitational encounter, becoming one of those rogue planets drifting eternally through intergalactic space. We have spoken extensively about the Sun's future, but there is a part of its story that deserves to be completed for the account to be whole: its birth. The Sun has not always existed. It has an origin as specific and verifiable as its destiny. Approximately 4.6 billion years ago, in a region of the Milky Way we would today recognize as the solar neighborhood, there existed a cloud of interstellar gas and dust several light years in diameter. That cloud, like many similar clouds in the galaxy, was composed mainly of hydrogen and helium, with small quantities of the heavier elements that previous generations of stars had dispersed into interstellar space in their deaths. Something perturbed that cloud. Perhaps it was the shock wave from a nearby supernova, the explosion of a massive star that compressed the cloud until triggering its gravitational collapse. Perhaps it was a density perturbation from crossing a galactic spiral arm of the Milky Way. Whatever the cause, the cloud began to collapse under its own weight. The collapse of a molecular cloud to form a star is a process astronomers can observe today in various regions of the galaxy. Stellar nurseries, like the famous Orion Nebula visible to the naked eye as a faint patch in the constellation Orion, are regions where clouds of gas and dust are fragmenting and collapsing to form new stars and new planetary systems right now. When the cloud that would become the Sun began to collapse, it fragmented into multiple local collapse regions. Each fragment would eventually form a different star. The Sun is one of those fragments, perhaps not the only one that formed from that original cloud. It could have stellar siblings, stars that were born from the same material at the same time, though by now they are scattered across the galaxy so far that identifying them without very precise chemical composition analyses would be impossible. The fragment that would become the Sun collapsed over the course of a few million years. As it collapsed, it conserved the angular momentum of the rotating cloud and flattened into a disk, the protosolar nebula. Most of the material fell toward the center, where pressure and temperature rose until nuclear fusion began. The Sun ignited. In the disk surrounding the newly formed Sun, dust particles collided and adhered, forming planetesimals that in turn collided to form planets. Earth and the other planets formed in the first 100 million years of the solar system's history, practically in an instant in cosmic terms. The current solar system, with its architecture of planets in their specific orbits, stabilized in its current configuration approximately 4 billion years ago. The Sun that shines today is the result of all that process. A process that began with a perturbation in a cloud of gas and dust and that in a few million years produced a star that would shine for another 4.6 billion years. And the same process is occurring right now in other parts of the galaxy, producing new stars and new planetary systems that in billions of years could follow paths similar to ours. In recent decades, astronomers have discovered thousands of exoplanets orbiting other stars. And among those stars there are some in advanced stages of their evolution, stars that are already red giants or that have already become white dwarfs. Studying those systems gives us a direct view of what will happen to ours in the future. Red giant stars are difficult to study in terms of their planets because the star's expansion enormously complicates planet detection by conventional methods. However, astronomers have confirmed the existence of planets orbiting some red giants, and studies of those systems show that the planets surviving the red giant phase are those that were initially far enough from the star to avoid being swallowed during maximum expansion. White dwarfs with planets are especially interesting. As mentioned, many white dwarfs show in their atmospheres traces of heavy elements that can only be explained by the accretion of planetary material. But in addition, astronomers have begun detecting intact planets orbiting white dwarfs at distances comparable to those that the outer solar system planets currently have from the Sun. In 2020, astronomers for the first time detected a Jupiter-sized planet orbiting a white dwarf at only 2 astronomical units. The existence of that planet so close to the white dwarf, when the original star was much larger, raises interesting questions about its history. Did it migrate inward after the star became a white dwarf? Did it survive in a wider orbit and then get displaced? Is it possible that in that system there were Earth-like planets that were destroyed during the red giant phase? Available data do not allow answering those questions with certainty, but they open perspectives on the diversity of what can happen in the future of systems like ours. The observation of planets around white dwarfs also has implications for the question of whether life can exist in those systems. White dwarfs emit radiation, though much less than main sequence stars. A planet in the habitable zone of a white dwarf, which would be very close given the little luminosity of the dwarf, would receive enough energy to maintain liquid water. But that habitable zone would not be stable for long, because the white dwarf continuously cools and the habitable zone shifts inward as luminosity decreases. If life existed on a planet around a white dwarf, it would have to be life that adapted to conditions changing on timescales of millions of years, which is fast in geological terms but possibly manageable in evolutionary terms if the changes are gradual enough. If Jupiter is the guardian of the solar system, Saturn is its jewel. Saturn's ring system is one of the most beautiful structures in the solar system and possibly one of the most photogenic objects in the observable universe. And it turns out those rings are temporary, a feature of Saturn that will exist only during a relatively brief period of the solar system's history. Saturn's rings are composed mainly of ice and rock particles ranging in size from dust grains to building-sized blocks. They extend from approximately 7,000 kilometers above Saturn's surface to about 80,000 kilometers away, but have an average thickness of only 10 meters in the thinnest regions. They are extraordinarily thin compared to their radial extent. The rings have an estimated age of between 10 and 100 million years, making them young in solar system terms. They are believed to have formed when a comet or asteroid got too close to Saturn and was destroyed by the planet's tidal forces. Or perhaps they were the result of a collision between 2 of Saturn's moons. In any case, they are a geologically recent structure, and they are disappearing. Ring particles interact with Saturn's magnetic field and the planet's ionosphere, and are gradually attracted to Saturn's equator where they fall in what is called ring rain. This process is consuming the rings at a rate suggesting they will disappear in approximately 100 million more years. If you were observing the solar system 100 million years ago, when dinosaurs dominated Earth, Saturn would not have had the rings it has today. If you observe the solar system 100 million years from now, when the Sun is starting its slow final main sequence transition, Saturn also will not have rings. The beauty we see today in images of Saturn is a temporary beauty, a phenomenon occurring at the exact moment we exist to see it. There is something in that which invites contemplation. Most of the things we consider permanent are temporary on the appropriate time scale. Continents move. Mountains erode. Oceans change shape. Species evolve and go extinct. And Saturn's rings, that structure that looks eternal and immutable in the photograph we have all seen, will disappear before the Sun even begins to age dramatically. Our galaxy has been forming stars for approximately 13 billion years, since shortly after the Big Bang. In that time, it has gone through different periods of star formation, some more active and some quieter, depending on the availability of cold gas that could collapse under gravity to form new stars. The first stars of the universe, called population 3 stars, were very different from the stars we see today. They formed from primordial gas composed almost exclusively of hydrogen and helium, without the heavy elements that today enrich the interstellar medium. As a consequence, they were extraordinarily massive, much more massive than any star we see today, and lived only a few million years before exploding in supernovae that scattered into space the heavy elements they had forged in their cores. Those first supernovae enriched the interstellar medium with carbon, oxygen, nitrogen, silicon, iron, and all the other elements of the periodic table beyond helium. The second generation of stars, formed from gas already enriched by those supernovae, could therefore have rocky planets. And the third generation, which includes the Sun, has such a richness of heavy elements that it allows the formation of Earth-like planets and the chemistry that makes life as we know it possible. The Sun is therefore the product of at least 2 previous cycles of star formation and death. Every atom of iron in Earth's core was forged in the violent death of a massive star more than 5 billion years ago. Every atom of carbon in any organic molecule of any living being on this planet has that same history. When the Sun dies in the distant future and expels its outer layers into interstellar space, it will contribute to that same enrichment process. The material it expels, rich in carbon and oxygen manufactured in its interior during its lifetime, will enrich the galaxy's interstellar medium. And eventually, that material could collapse again to form new stars and new planetary systems, continuing the cycle that has given rise to everything that exists in the universe today. The universe's history is largely the history of those stellar generation cycles, of the slow accumulation of heavy elements in the interstellar medium, of the progressive building of the chemical complexity that makes organic molecules, life, and eventually the consciousness that can ask about this process possible. The Sun is a point in that process. A specific point, a named point with known history, a point of which we are the product. But only one point among the 400 billion stars of our galaxy, which is itself only one among 2 trillion galaxies in the observable universe. That perspective of scale does not diminish the Sun's importance to us. It amplifies it. Because in all that immensity, this specific Sun, with this specific planetary system, produced the exact conditions for the emergence of life that eventually wondered about its star's fate. That is no small thing. There is a perspective on solar energy that completely transforms the way of thinking about the fossil fuels that human civilization has been burning since the Industrial Revolution. When you burn coal or oil or natural gas, you are burning sunlight. Not today's sunlight, but sunlight from millions of years ago. Fossil fuels are organic matter, remains of living organisms that lived between 60 and 300 million years ago, compressed and transformed under the heat and pressure of the rock layers that covered them. Those living organisms captured energy from the Sun through photosynthesis and stored it in organic molecules. When they died and were buried and transformed into fossil fuels, that solar energy was stored in the chemical structure of those compounds. When you burn a liter of gasoline, you are releasing solar energy that was captured by marine organisms approximately 150 million years ago in the Middle Jurassic period. The heat that liter produces in a car engine is solar heat from the time of the dinosaurs. That perspective makes burning fossil fuels literally a process of releasing past sunlight. And it also makes the idea that burning could alter the planet's climate conceptually coherent. We are adding to the atmosphere the carbon that those organisms had extracted from the air millions of years ago, changing atmospheric composition at a rate unprecedented in recent geological history. The solar energy we use today directly, through solar panels or simply through the Sun's heat on our buildings and our agriculture, is on the other hand the energy of the Sun right now, what the Sun is producing at this moment by burning hydrogen in its core. It is the most recent available energy, as opposed to fossil energy, which is solar energy stored for millions of years. The Sun has been sending energy to Earth for 4.6 billion years. That energy has been captured, stored, transformed, and released in countless cycles since life began. The plants photosynthesizing today are converting sunlight into organic compounds. The animals eating those plants are converting those compounds into movement and heat. Fossil fuels are just one of the many forms in which that solar energy has been stored and released over time. The light that will arrive from the sun tomorrow is only the most recent chapter of an energy story that started 4.6 billion years ago and will continue for another 5 billion. The sun is the most durable energy source Earth has had, and will continue to be so for far longer than any other process could be sustained. The universe is cooling. Not dramatically or perceptibly on human timescales, but the universe's temperature has decreased enormously since the Big Bang and will continue to decrease in the future. Just after the Big Bang, the universe's temperature was billions of degrees. As the universe expanded, that temperature dropped. 380,000 years after the Big Bang, when the cosmic microwave background was released, the temperature had fallen to approximately 3,000 degrees. Today, 13.8 billion years later, the cosmic microwave background temperature is approximately 2.7 Kelvin, less than 3 degrees above absolute zero. In the future, as the universe continues expanding, that temperature will keep falling. In 1 trillion years, when the last main sequence stars are dying and only white dwarfs, neutron stars, and black holes remain, the cosmic microwave background temperature will have fallen to tenths of a Kelvin. In 100 trillion years, when even the last red dwarfs have gone out, it will be at thousandths of a degree above absolute zero. The universe cools because it expands. Cosmic microwave background photons lose energy as space stretches, their wavelengths increase, and their effective temperature decreases. It is as if visible light photons from the sun progressively became infrared photons, then microwave, then radio, as energy is diluted in ever greater space. The sun, during its life, is a small local exception to this universal cooling trend. It heats its immediate surroundings, produces photons that travel outward and warm the planets orbiting it. But on the universe's scale, that local warming is insignificant. The universe cools on average, and stars are only temporary heat sources in an increasingly cold hole. When the sun becomes a white dwarf and begins to cool, it will join the universe's general trend. It will no longer be the heat generator it is today. It will be an object slowly radiating the residual heat of its active life, becoming progressively colder until eventually, on timescales of quadrillions of years, its temperature becomes indistinguishable from the surrounding universe's temperature. The sun, in its death, will become part of the universe's general cold. It will not disappear. It will continue to exist as a massive object distorting space-time around it. But it will cease to be an active source of heat and light. It will become a passive object in a passive universe, drifting toward the thermal equilibrium that is the final fate of everything that exists in the cosmos. Tonight there is no visible sun from where you are. Earth has rotated until this hemisphere faces space away from the sun, and in that darkness it is easy to forget the sun exists, that it is there, 150 million kilometers away, shining with its usual intensity, illuminating the other side of the planet. The sun you cannot see tonight is burning 4 million tons of hydrogen per second, as always. It is sending outward in all directions a flow of photons traveling at 300,000 kilometers per second, of which a tiny fraction will reach this part of Earth at dawn. The photons that will illuminate your tomorrow are at this moment already halfway there, traveling through the space between the sun and Earth during the time you have been sleeping. Night is not the sun's absence. It is only the angle from which we see it. Earth is always in the sun, always receiving its light and heat on some part of its surface. Night and day are a consequence of the planet's rotation, not the sun switching off. And the sun that will shine tomorrow is the same sun that has shone for 4.6 billion years. It is the same sun under which the first microorganisms evolved in the primitive oceans. The same sun that the first human beings saw on the African plains. The same sun that illuminated the first civilizations in Mesopotamia and Egypt, that warmed Alexander's campaigns and Columbus's ships, that lit Galileo's first experiments and Newton's first equations. In 5 billion years it will begin to change. But tonight, in the darkness, it has not changed yet. It is still the same star as always, shining with its usual constancy, storing in its core the fuel remaining to keep doing so for a time that surpasses any human conception of what a long time is. The light of tomorrow's sun took 8 minutes to arrive, and the photons composing it were generated in the solar core hundreds of thousands of years ago. They are messages from the past that will reach your eye tomorrow with their usual normalcy. There is something serene in that chain of continuity. The sun, time, light, darkness, the dawn that will come. Everything continues in its rhythm, regardless of what we think about it, and will continue doing so for more time than any mind can represent. Sleep is coming now, and the sun keeps shining on the other side of the planet as it always has done, as it will keep doing when you wake. There is a way of experiencing sunlight that is rarely practiced but that transforms ordinary moments into something much larger. It requires only a pause and a specific thought. Every photon reaching your eyes from the sun is a message that began its journey in the solar core over 100,000 years ago. The photon was born as a gamma ray in a nuclear fusion reaction, bounced for 100,000 years through the dense solar interior, losing energy gradually with each absorption and re-emission, until it finally escaped from the photosphere as visible light. Then it traveled for 8 minutes through empty space, crossed Earth's atmosphere in a fraction of a second, and arrived at your retina. That photon has existed longer than all of recorded human history. It was created before the first permanent human settlements, before the invention of writing, before the agricultural revolution that made cities possible. It predates every religion, every empire, every language that has ever been spoken. It traveled silently through the solar interior while civilizations rose and fell, while species evolved and went extinct, while continents shifted imperceptibly on their tectonic plates. And now it has ended its journey, absorbed by the light-sensitive cells of a human eye, converted into an electrical signal, interpreted by a brain as the sensation of warmth and light. 100,000 years of journey ending in a single moment of perception. This perspective does not change the physics of how sunlight works, but it changes the experience of receiving it. Knowing that the light warming you on a spring afternoon has been traveling since the last ice age gives every moment in the sun a depth that pure sensation cannot provide. The sun's death, 5 billion years away, will be the end of that long chain of photon journeys from core to Earth. Until then, the chain continues, unbroken, generating 4 million tons of energy per second, sending messengers across space that arrive 8 minutes later to illuminate a world that depends entirely on their delivery. In that sense, every sunrise is not just the return of the light. It is the continuation of a process that has been running without interruption for 4.6 billion years, and that will keep running for 5 billion more. The sun's habitable zone, the region around it where liquid water can exist on a planet's surface, is not a fixed property of the solar system. It moves outward as the sun brightens, and that movement has profound implications for the history and future of life in the solar system. When the sun first formed 4.6 billion years ago, its habitable zone was closer in than it is today. The early sun was about 30% dimmer than today. A planet at Earth's current orbit would have been too cold for liquid water. This creates an apparent paradox. If the early sun was dimmer, how did Earth have liquid water and life 4 billion years ago? The answer likely involves a combination of factors. Higher concentrations of greenhouse gases like carbon dioxide and methane in the early atmosphere, possibly higher geothermal heat flow, and perhaps other mechanisms that kept Earth warm despite the dimmer sun. Understanding this paradox is one of the active areas of research in early Earth science. As the sun has brightened over its history, Earth has remained in the habitable zone partly through its own geological and biological processes. Plate tectonics regulates the long-term carbon cycle, drawing down carbon dioxide through silicate weathering when temperatures rise and releasing it through volcanism when temperatures fall. Life itself has participated in regulating the atmosphere, most dramatically in the Great Oxidation Event when photosynthetic microbes flooded the atmosphere with oxygen about 2.4 billion years ago. In the future, as the sun continues to brighten, Earth will eventually be pushed out of the habitable zone from the inner edge. Models suggest this will happen within approximately 1 to 2 billion years, when the planet becomes hot enough for the runaway greenhouse to take hold. But as Earth loses its habitability, other worlds may enter the habitable zone. Mars sits just outside the current habitable zone's outer edge. As the sun brightens, Mars could find itself in the zone for a period. The question of whether Mars could harbor life during that period is complicated by its thin atmosphere, which it largely lost due to the absence of a global magnetic field, and by its small size, which limited geothermal heating. But the window of opportunity for liquid water on Mars in the future is real. The outer moons, Europa, Enceladus, Titan, will see their environments transform dramatically as the sun enters its red giant phase. Worlds that today are frozen will receive heat that could liquefy their surfaces. The habitable zone during the red giant phase will stretch far into the outer solar system, potentially creating brief windows of habitability that have never existed before in those cold, distant worlds. Life, if it exists or arises on those worlds, would have billions of years to adapt to their current cold conditions before the sun's expansion begins to warm them. And it would have millions of years during the warming period to either adapt or migrate or perish. The story of life in the solar system, if there is more of it than we know of today, is not just Earth's story. It is a story that plays out across billions of years and many worlds. In the very long run, after the sun has become a white dwarf and the planetary nebula has dispersed, after the outer planets have settled into their expanded orbits and the solar system has grown quiet and cold, there will still be matter. The matter of the sun, the matter of the planets, the matter of everything that ever existed in this system does not disappear. Conservation of matter and energy is one of the most fundamental principles of physics. What was once hydrogen in the protosolar nebula becomes helium in the sun's core, then carbon and oxygen, then the material of the planetary nebula, then the white dwarf plus the dispersed gas. At every stage, matter and energy are transformed but not created or destroyed. The accounting always balances. The dispersed gas of the planetary nebula will mix with interstellar gas, travel through the Milky Way, and eventually, in hundreds of millions to billions of years, become part of a new molecular cloud that collapses to form new stars. The carbon and oxygen the sun manufactured in its core will be incorporated into new stars, new planets, potentially new chemistry, potentially new life. The atoms that today form the sun will, in the far future, be part of something else entirely. They may be in a star more massive than the sun that lives fast and dies in a supernova. They may be in a red dwarf that lives for trillions of years. They may form rocky planets orbiting those stars, or float freely in interstellar space for billions of years before being incorporated into anything. The atoms currently in your body follow the same principle. They were forged in stellar interiors before the sun existed. They will continue existing long after the sun is gone. You are made of matter that has been through multiple cosmic cycles already, and will go through many more. That continuity, that persistence of matter through transformation after transformation, across timescales that dwarf any individual existence, is perhaps the most astonishing thing that physics reveals about the universe. Nothing is wasted. Everything is recycled. The sun's death is genuinely the seed of something new, in the same way that the death of earlier stars was the seed of the sun itself and of the earth and of you. After having traveled through time, from the sun's birth to its death and beyond, something clarifies. The present is not just a point on a timeline. It is the only point from which anything can be experienced. The sun of 4.6 billion years ago was not experienced by anyone. There was no one here to see it. The sun of 5 billion years from now will not be experienced by any human being. There will be no one here to see it under the conditions we know today. The only sun that has been and will be seen by conscious beings on this planet is the sun of now, the sun of the last billions of years of complex life, and the sun of the next hundreds of millions of years remaining before conditions become incompatible with life as we know it. That is the sun that exists in experience. The historical sun, the future sun, are constructs of thought, extrapolations of physics. The real sun, the one that is experienced, is this one, the present one. Science gives us the extraordinary privilege of understanding that sun beyond immediate experience, of knowing what it is and what it has been and what it will be. But that knowledge enriches experience rather than replacing it. Knowing the sun is 4.6 billion years old does not make its light less warm. Knowing it will die in 5 billion years does not make tomorrow's sunrise less beautiful. Knowledge adds layers of meaning to experience without eliminating the experience itself. The sun that will rise tomorrow is at the same time a mediocre star in the Milky Way's Orion Arm, one of 400 billion similar suns, and the source of everything that on this planet moves, grows, feels, and thinks. Those two truths do not contradict each other. They are simply two ways of seeing the same object, two scales from which it is possible to contemplate something genuinely extraordinary from either of them. Tonight you have contemplated the sun from the cosmic scale. You have seen its birth, its life, its future. You have understood why it will shine another 5 billion years and why it will eventually stop shining. You have learned the physics that keeps it burning and the physics that will eventually extinguish it. The sun will die within approximately 5 billion years, but there are stars in our galaxy that will live far longer and stars that have already died long ago. Massive stars, those with between 10 and 100 times the sun's mass, shine with an intensity that exhausts their fuel in millions rather than billions of years. A star 40 times the sun's mass will live only a few million years before exploding in a supernova. This is why, even though massive stars are the brightest objects in the universe, they are also the most ephemeral. There is no time for planets to form around them, or if they form, no time for anything complex to evolve on those planets before the star explodes. Small stars, the red dwarfs with between 8 and 40% of the sun's mass, will live an incomparably longer time. A star 1/4 the sun's mass will live approximately 200 billion years, nearly 15 times the current age of the universe. The smallest red dwarfs could live for trillions of years. This has extraordinary consequences. Red dwarfs are the most abundant stars in the galaxy, representing approximately 70% of all stars. And they will live so long that they have the potential to host life for periods that are almost incomprehensible from a human perspective. If planets around red dwarfs are habitable, and there are good arguments both for and against, then those stars represent the future of life in the galaxy. In the far future, when the sun is a cooling white dwarf, red dwarfs will still be active stars. Within 10 trillion years, when the last red dwarf finally exhausts its fuel, the sun will have been a white dwarf for many billions of years already. The last stars to go out in the galaxy will be these tiny, long-lived red dwarfs. After the last star goes out, the universe will enter what physicists call the degenerate era. Only compact objects will remain: white dwarfs, neutron stars, and black holes. None produces significant new quantities of energy. All are gradually losing what they have to space. The universe will become progressively colder, darker, quieter. But even in the degenerate era, the universe will not be completely inactive. Black holes will continue evaporating slowly through Hawking radiation. This process is so slow that a solar mass black hole would take 10 to the power of 67 years to evaporate. But on sufficiently long timescales, even the supermassive black holes at galaxy centers will eventually evaporate, and with them will disappear the last significant reservoir of available energy in the universe. The Sun is not a static, uniform object. It has a surface in constant motion, magnetic fields that tangle and reconnect, and episodes of violent activity that can affect the entire solar system. Sunspots are the most visible manifestations of the Sun's magnetic activity. They are regions of the photosphere where the magnetic field is especially intense and where the surface temperature is slightly lower than in surrounding regions, making them appear darker. In sunspot regions, the intense magnetic fields inhibit the convection of hot gas from the interior, locally reducing surface temperature from approximately 5,500 degrees Celsius to about 4,200. Sunspots follow an approximately 11-year activity cycle, moving through periods of maximum when dozens of large spots can appear on the solar surface simultaneously, and periods of minimum when the solar surface can be completely spotless for days or weeks. This 11-year cycle corresponds to a deeper 22-year magnetic cycle in which the Sun's magnetic field polarity reverses. Solar flares are the most energetic events of solar activity. They occur when tangled magnetic fields near sunspots suddenly reconnect, releasing in minutes or hours an amount of energy that can exceed all the energy the Sun emits in an entire second. That energy is released as intense electromagnetic radiation and charged particles accelerated to relativistic speeds. Coronal mass ejections are even more massive events in which clouds of solar plasma of billions of tons are launched into space. When those clouds reach Earth, they interact with the magnetosphere, producing geomagnetic storms that can damage satellites, disrupt radio communications, and in extreme cases cause failures in electrical grids. The Carrington event of 1859, the most intense solar activity event on record, was strong enough to produce auroras visible in the tropics and to disable telegraph systems across Europe and North America. As the Sun ages over the next billions of years, its magnetic activity and the frequency and intensity of its flares will change. During the red giant phase, when the Sun's convective envelope is much deeper and more extensive, magnetic fields could organize in different ways, and surface activity could be radically different from what it is today. The Sun will die as a white dwarf, as we have seen, because its mass is insufficient to produce the more dramatic processes that occur when more massive stars exhaust their fuel. But elsewhere in the galaxy, right now, much more massive stars are following evolutionary paths that end in far more violent ways. A star with between 8 and 20 solar masses that exhausts its nuclear fuel does not have enough mass to become a black hole, but does have too much to stop at the white dwarf state. When that star's iron core collapses under its own weight, electrons and protons in its atoms fuse under extreme pressure to produce neutrons and neutrinos. The core collapses in a fraction of a second until neutron degeneracy pressure, a quantum analog of the electron degeneracy pressure that maintains white dwarfs but incomparably more intense, stops the collapse. The result is a neutron star, a city-sized object with a mass greater than the Sun's. The sudden collapse of the core produces a shock wave that propagates outward through the star's outer layers, expelling them into space in an explosion called a supernova. A supernova can shine momentarily with luminosity comparable to an entire galaxy, being visible at distances of millions of light years. The remains of that explosion disperse into interstellar space, enriching it with heavy elements manufactured in the star's interior and with elements produced in the explosion itself. Stars more than 20 solar masses can undergo an even more extreme collapse in which not even neutron degeneracy pressure can stop it. The result is a black hole, an object with so much mass concentrated in so little volume that the escape velocity from its surface exceeds the speed of light. No signal can escape from beyond a black hole's event horizon. They are objects that exist in physics but represent the limit of what general relativity can describe without producing mathematical singularities. The Sun will not produce either a neutron star or a black hole. Its mass is insufficient for that. But there are stars in the Milky Way right now in the final stages of their lives that will produce those objects when they die. Betelgeuse, the bright red star at the shoulder of Orion, is a red supergiant that could explode in a supernova at any time in astronomical timescales, within the next 100,000 years. When it does, it will be visible in daylight from Earth for weeks, the nearest supernova we would have observed since SN 1987A in the Large Magellanic Cloud. That diversity of stellar fates, white dwarfs, neutron stars, black holes, reflects the diversity of masses with which stars are born. And each type of fate has its own physics, its own time scale, its own consequences for the surrounding environment. The galaxy is full of all these objects in different stages, like a photo album of different moments in stellar lives that we can see simultaneously because each star is different from the others. There is a truth about what we are that astrophysics has established with such solidity that it deserves to be contemplated slowly. The atoms of your body, with the exception of hydrogen, were not formed in the Big Bang. They were formed in the interior of stars that lived and died before the sun was born. The carbon that forms the basis of all organic molecules in your body was forged in the core of medium-mass stars like the Sun in their red giant phase. The oxygen, also forged in those same stars. The nitrogen, in similar processes. The iron in your hemoglobin, the minerals in your bones, the silicon in the sand you walk on when strolling a beach, all of it was forged in the interior of massive stars that lived and died in supernovae billions of years ago. Astronomers call this process stellar nucleosynthesis. The physics governing nuclear fusion in stars is the same physics that built the atoms composing you. You are, literally, the product of the deaths of stars. Every atom of your body has a history traceable to a stellar furnace, to a supernova explosion, to a long journey through interstellar space until the gas and dust cloud that collapsed to form the Sun and planets 4.6 billion years ago. That debt to dead stars is also a promise for future stars. When the Sun dies and expels its planetary nebula into space, the atoms that have been part of its photosphere, that have been part of the planets, that may at some point have been in living organisms on this planet, will disperse through interstellar space. They will mix with the gas and dust already existing between stars. And in tens or hundreds of millions of years, they could collapse again under gravity to form new stars and new planetary systems. The iron in your blood could end up in the core of a planet in a solar system forming 6 billion years from now. The carbon in your cells could end up in the atmosphere of a world that in that far future perhaps also harbors life. Matter does not disappear. It recycles through the cosmos in cycles longer than Earth's history of life, but as real and verifiable as any geological cycle we observe today. We are part of a cycle that started before Earth existed and will continue long after it has ended. We are not the beginning or the end of that story. We are a chapter, extraordinarily specific and extraordinarily improbable, in a story of transformations that began in the Big Bang and will continue until the last black hole in the future universe evaporates into darkness. The sunlight reaching Earth carries energy in the form of photons spanning a wide range of wavelengths, but concentrated in the visible spectrum. That concentration is not a coincidence. It is the result of the sun's surface temperature, which determines the peak wavelength of radiation according to a physical law called Wien's displacement law. The sun's surface temperature of approximately 5,500 degrees Celsius causes it to emit most intensely in the yellow-green region of the visible spectrum, around 550 nanometers wavelength. That is almost exactly the region where the human eye has its peak sensitivity. It is also close to the region where photosynthesis is most efficient, where water is most transparent, and where Earth's atmosphere transmits most readily. Whether that alignment represents design, coincidence, or evolutionary adaptation to available light is a philosophical question that physics does not answer. What physics can say is that organisms on Earth, including humans, are exquisitely adapted to the specific light the sun produces. Our eyes, our plants, our photosynthetic cells, our vitamin D synthesis all operate at wavelengths tuned to the sun's output. When the sun becomes a red giant, it will be much cooler at the surface, perhaps around 3,000 degrees, and its peak emission will shift toward the red and infrared. The character of the light it emits will change fundamentally. The intense yellow-white light of today will give way to a dim orange-red glow that illuminates the surviving outer worlds with a different quality. Photosynthesis, adapted to today's solar spectrum, would not function the same way under red giant light even if the temperatures were somehow habitable. The white dwarf phase will produce yet another type of light. A newly formed white dwarf shines intensely in the ultraviolet, far too energetically for most biological molecules to survive. As it cools over billions of years, its emission shifts through visible wavelengths, eventually dimming to the orange and red end of the spectrum. The light of a very old white dwarf is faint and red, a whisper compared to the voice the sun has today. Each phase of the sun's life produces its own quality of light, its own signature in the spectrum that astronomers can use to identify stars at different evolutionary stages. The stars we see in the sky tonight are a population at many different life stages, each shining with the color and brightness appropriate to where they are in their journey from nebula to white dwarf or neutron star or black hole. The sun's yellow-white light is the light of a star in its prime, a star in thermally comfortable middle age, burning hydrogen steadily. That is the light Earth evolved under. That is the light life here depends on. And recognizing that dependency, understanding how specific and how temporary the conditions enabling it are, makes the experience of sunlight something different than a mere physical sensation. It would be incomplete to speak of the sun's energy contribution to Earth without acknowledging that Earth has its own internal energy source: the heat from radioactive decay in its interior and residual heat from its formation. When Earth formed 4.5 billion years ago, the accretion of material released enormous amounts of kinetic energy as heat, and the differentiation of the planet into core, mantle, and crust released additional heat as dense iron sank toward the center. That primordial heat has been slowly leaking out through the planet's interior ever since, driving plate tectonics, volcanism, and the geological processes that have continuously resurfaced and reshaped Earth's exterior. Radioactive decay of isotopes like uranium, thorium, and potassium in the mantle and crust provides ongoing heat generation, supplementing the residual primordial heat. Together, these sources drive the geological activity that maintains plate tectonics, the process by which Earth's outer shell is continuously recycled into the mantle and new crust is generated at mid-ocean ridges. Plate tectonics is fundamental to Earth's long-term habitability. It regulates the long-term carbon cycle through volcanic outgassing and silicate weathering. It generates the continental diversity of environments that has driven evolutionary innovation throughout life's history. It maintains the magnetic field by driving convection in the liquid outer core, and that magnetic field deflects the solar wind that would otherwise strip away the atmosphere. When the sun finally reaches its red giant phase and begins to heat Earth's exterior dramatically, Earth's interior will still be producing its own heat. That interior heat will continue independently of the sun for billions of years. Even on a world whose surface has been scorched by the expanding sun, the geological processes driven by interior heat could continue for a long time. This separation of interior and exterior heat sources means that even after the sun's influence on Earth's surface has become catastrophically large, the planet's interior will continue its slow geological clock. Volcanoes may still erupt into a superheated atmosphere. The core may still generate a magnetic field protecting the planet from the solar wind, however brutal that wind becomes. Earth will not be geologically dead even when it is biologically dead. Understanding this helps clarify what the sun's death actually kills. It kills the specific conditions that enable the chemistry of life as we know it: liquid water, moderate temperatures, protection from excessive radiation, stable seasons, nutrient cycling driven by flowing water. It does not kill the planet as a geologically active object. Earth will remain a world of sorts, just not a world for life. There is one aspect of the Earth-Sun system that is rarely included in discussions of the Sun's fate, but that deserves mention: the extraordinary role the Moon plays in Earth's stability as a habitable planet. The Moon is unusually large compared to Earth. Most natural satellites are small compared to the planet they orbit. The Moon has approximately 1% of Earth's mass, making it the largest satellite relative to its planet in the solar system, with the exception of the Pluto-Charon system, which is now classified as a dwarf planet. The Moon's origin is itself an extraordinary story. According to the most widely accepted model, approximately 4.5 billion years ago, when Earth was barely tens of millions of years old, a Mars-sized object called Theia collided with Proto-Earth at an oblique angle. The impact was violent enough to vaporize parts of both bodies and hurl enormous quantities of material into space, which eventually aggregated to form the Moon. That violent origin had a stabilizing consequence that seems paradoxical. The Moon's gravity exerts tidal forces on Earth that stabilize the tilt of Earth's rotational axis. Earth's axis is tilted approximately 23 degrees relative to the plane of its orbit around the Sun. That tilt is what produces the seasons. Without the Moon stabilizing that tilt, the axis could vary chaotically between nearly 0 degrees and more than 85 degrees on timescales of millions of years, producing climate variations so extreme they would have severely hindered the evolution of complex life. Mars, which lacks a large moon, has had a rotational axis that has varied between 0 and 60 degrees in the past. Those variations have produced dramatic climate changes on Mars throughout its history, and are one of the reasons Mars, though it had liquid water on its surface in the past, has today the arid and cold appearance we observe. As the Sun evolves and the Moon's distance from Earth gradually increases through tidal effects that transfer angular momentum from Earth's rotation to the Moon's orbit, the Moon's stabilizing effect on Earth's axis will change. On timescales of billions of years, the Moon could be far enough away that its stabilizing effect is significantly reduced. But by that point, Earth's habitability will have ended for other reasons related to the Sun's warming, so the Moon's role in the long-term story of the solar system is fundamentally a story of the first billions of years of life on Earth, not of its ending. 5 billion years. Let us try to feel that number rather than just state it. A human lifetime, generously, is about 100 years. 5 billion years is 50 million human lifetimes. If you stretched a single lifetime across the length of a football field, and then laid 5 billion of them end to end, you would need a line running roughly 1 million kilometers, about 2.5 times the distance from the Earth to the Moon. That is the time remaining before the Sun begins its transformation. The time in which all of recorded human history has occurred, the 5,000 years from first writing to this present moment, is an almost infinitesimally small fraction of that remaining time. The entire span of complex multicellular life on Earth, 550 million years, is about 11% of that remaining time. The age of the universe itself is only about 2.7 times that remaining time. In that context, the death of the Sun is not an imminent threat or even a distant concern in any practical sense. It is something that will happen so far in the future that no continuity of any kind exists between us and the moment of its occurrence. The Sun that will die in 5 billion years is, from the perspective of lived experience, as abstract as the center of another galaxy. But knowing it will happen, understanding the physics of why and how, places the Sun we experience today in a different frame. The Sun shining this morning is not eternal. It is temporary, on a cosmic scale. It is using up resources, burning through fuel, following a trajectory that will eventually take it to a very different state. That temporariness, that finite nature of the Sun's current phase, is not a sad fact. It is simply a fact, and one that adds rather than subtracts from the experience of the Sun in the present. Knowing that a friend will eventually die does not diminish the friendship. Knowing that a season will end does not make you enjoy it less. The finite nature of things is often the source of their preciousness, not their diminishment. The sun rises every morning. It will keep doing so for 5 billion more years. That is, from any perspective that matters to living beings, essentially forever. Tonight it is on the other side of the planet, shining on different oceans and different continents. Tomorrow it will be back. That is what the sun does. That is what it has done for 4.6 billion years. That is what it will do for 5 billion more. At the very end of the sun's story, after the white dwarf has cooled for trillions of years, there will be what astronomers call a black dwarf, an object of roughly Earth size, half the current sun's mass, at a temperature barely above absolute zero, invisible and cold in the darkness of whatever the universe will be by then. That object will drift through space, feeling the gravity of whatever is around it, gradually being perturbed by the gravitational fields of other objects as the long epochs pass. The galaxies will have merged, or dispersed, or both. The cosmic web that structures the universe today will have been dissolved by the relentless expansion of dark energy. The black dwarf will move through a universe far emptier and far colder than anything alive today could experience. There will be no signal on that black dwarf, no trace visible to any theoretical observer of what it once was. Nothing that says, this was once a star that shone for 10 billion years. This was once surrounded by 8 planets, one of them harboring life for 4 billion years. Nothing that records the civilizations that arose on that third planet, the thoughts those civilizations had, the questions they asked about the sun's fate, the knowledge they accumulated. And yet, in the most fundamental physical sense, the conservation of information that quantum mechanics requires means that information about all of that still exists, encoded in the quantum state of the universe with a completeness no observer could access, but that is mathematically real. The past is not gone. It is inaccessible. This is perhaps the strangest comfort physics offers, that the universe, at the deepest level, is a system that does not forget. Every moment that has occurred, every configuration of matter and energy that has briefly come together and then dissolved, is in some sense still present in the quantum state of the cosmos. Not recoverable, not experienceable, but not simply gone either. The sun will die. The white dwarf will cool. The black dwarf will drift in silence through a universe that has long since moved on. And in that silence, encoded in ways no mind can access, will be the memory of 4.6 billion years of a star doing what stars do: burning, warming, making life possible, and then ending. Throughout human history, the sun has been simultaneously the most fundamental object of astronomical study and the most universal source of inspiration for poetry and art. That double presence, as scientific fact and cultural symbol, says something about how human beings relate to the cosmos. Ancient Greek thinkers debated the sun's nature with remarkable sharpness, given that they lacked the instruments we have today. Anaxagoras proposed in the 5th century BCE that the sun was a mass of incandescent iron the size of the Peloponnese Peninsula. Aristarchus of Samos, in the 3rd century, proposed that Earth orbited the sun and not the reverse, anticipating Copernicus's heliocentric model by almost 2,000 years. Hipparchus calculated the distance to the moon with remarkable precision using only trigonometry and observations of lunar parallax during eclipses. But none of those thinkers could have imagined what modern astronomy has revealed: that the sun is one star among hundreds of billions in the Milky Way, that the Milky Way is one galaxy among 2 trillion in the observable universe, and that the sun has a past stretching back 4.6 billion years and a future extending 5 billion more. That perspective of scale, which makes the sun simultaneously smaller and more extraordinary than it seemed, is one of the great achievements of human thought. Modern solar physics has instruments those Greeks could not have imagined. Helioseismologists study the internal vibrations of the sun, sound waves propagating through its interior that on the surface produce oscillations of the photosphere detectable from Earth. Those oscillations allow reconstruction of the Sun's internal structure in the same way that terrestrial seismologists study Earth's interior from seismic waves produced by earthquakes. We know more about the Sun's interior than about Earth's interior, paradoxically, because the Sun's surface vibrates in ways that reveal its internal structure. Modern solar satellites, like NASA's Solar Dynamics Observatory or the Parker Solar Probe that has brought an artificial probe closer to the Sun than any before it, are revealing the physics of the solar corona, the Sun's outer atmosphere that reaches temperatures of millions of degrees while the solar surface is at only 5,500 degrees. Why the corona is so much hotter than the photosphere is one of the most active problems in solar physics, and its resolution could have implications for understanding plasma heating mechanisms in all sorts of astrophysical environments. There is something the Sun's story, taken seriously, asks of us. Not demanded, not required, but quietly invited by the perspective it offers. It asks us to notice it. Not to take it for granted in the way that constant things tend to be taken for granted, but to actually notice the light, the warmth, the daily rhythm it creates. The morning light that warms a room before you think to appreciate it. The long summer evenings where the light lingers. The winter sunrises where the low angle of light creates shadows of extraordinary length. All of it is the Sun, doing what it has done for 4.6 billion years, with complete reliability and complete indifference to whether anyone notices. It asks us to appreciate scale. The Sun is 4.6 billion years old. The life on Earth that the Sun makes possible is almost 4 billion years old. The complex multicellular life that the Sun has been warming for 500 million years has produced, in its most recent chapter, creatures capable of asking what the Sun is and what will become of it. That chain of causation, from stellar nursery to nuclear fusion to photosynthesis to evolution to consciousness to curiosity about the cosmos, is one of the most astonishing chains of causation in the known universe. And it asks, perhaps most importantly, for a certain comfort with impermanence. The Sun will die. Earth will become uninhabitable. The solar system will be reorganized beyond recognition. These are not tragedies awaiting us. They are facts about the nature of existence in a universe governed by physical laws that neither favor nor disfavor any particular arrangement of matter. The universe is not trying to preserve the conditions of life. It simply is what it is, changing according to its laws, with no intention in any direction. Finding peace with that, finding beauty in the temporary nature of all arrangements, including the arrangement that makes life and consciousness possible on this particular planet orbiting this particular star, is something the contemplation of the Sun's fate can offer. Not as consolation for a loss, but as a more accurate perception of what existence is. The Sun will rise tomorrow. It has done so without fail for 4.6 billion years. Every ancient sea creature that ever saw sunlight filtering through the ocean surface saw the same sun. Every dinosaur that ever raised its head toward the sky saw the same sun. Every human being who has ever lived has seen the same sun. Tomorrow you will see it too. That continuity, reaching through hundreds of millions of years and billions of lives, is one of the most extraordinary things about the planet we inhabit. Right now, while you are reading this in what may be the dark quiet of a night, the Sun is shining on another part of the world, burning 4 million tons of hydrogen per second, as it has for 4.6 billion years, as it will for 5 billion more. Its light is reaching the Pacific, reaching Asia, reaching Africa, warming the oceans and the land and the billions of organisms that depend on it. The darkness you are in is not the Sun's absence. It is your angle relative to it. You are on the shadowed side of a rotating planet, temporarily away from the light source that will return in a few hours as predictably as it has returned every morning throughout the history of life on this world. In those few hours, while you sleep, the Sun will not pause. Photons will continue arriving at the sunlit hemisphere. Carbon dioxide will continue being absorbed by leaves. Temperatures will continue rising with the dawn on the other side of the planet. The vast machinery of the sun-driven biosphere will continue its work as it does continuously, without any pause corresponding to human sleep schedules or human attention. When you wake, the sun will be there. It always is. It has always been. It will be for a time so long that it is, from the perspective of a human life, indistinguishable from forever. Knowing what will eventually happen to it, knowing the physics that governs its life and death, does not change the reliability of its return. It cannot change the warmth of tomorrow's light. It cannot diminish the sunrise that is already a few hours away. It can only add depth to the experience, the way all genuine understanding adds depth rather than diminishing wonder. The sun's story is, in the end, the context in which all of human experience occurs. Every thought, every feeling, every relationship, every achievement of human civilization has happened under this specific star at this specific phase of its life. The warmth enabling it all is not guaranteed by the laws of nature in general, but by the specific facts of this star, this distance, this planet, this moment in cosmic history. Tonight you are part of that specific configuration. Tomorrow you will be again. And for billions of years after the last human thought, the sun will keep shining, because stars do not need anyone to witness them to do what they do. That is the sun's final word on the subject, and perhaps the most calming one. The sun does not travel through the galaxy alone. It moves through the Milky Way at approximately 220 kilometers per second relative to the galactic center, completing one orbit around the galaxy approximately every 230 million years. In the course of that orbit, it passes through different regions of the galaxy with different stellar densities, different gas clouds, different levels of star-forming activity. The nearest star to the Sun is Proxima Centauri, a red dwarf approximately 4.2 light-years away. It is part of the Alpha Centauri triple system, which also includes Alpha Centauri A and B, both stars similar to the Sun though slightly different in mass and age. These neighbors are separated from us by a distance so large that even the fastest spacecraft ever built would take thousands of years to cross it. Proxima Centauri is a red dwarf, which means it will outlive the Sun by an enormous margin. When the Sun has become a cooling white dwarf, Proxima Centauri will still be on the main sequence, burning hydrogen steadily. It will continue for trillions of years after the Sun has gone dark. In that sense, our nearest neighbor will be one of the last lights to go out in our local corner of the galaxy. Proxima Centauri is known to have at least one planet, Proxima Centauri b, orbiting in its habitable zone. Whether that planet is actually habitable is debated. Red dwarfs produce intense flares that could strip away a planet's atmosphere, and a planet in the habitable zone of a red dwarf would orbit so close that it might be tidally locked, always showing the same face to its star. But the existence of a potentially habitable planet around our nearest stellar neighbor has profound implications for our understanding of how common habitable worlds might be. Tau Ceti, a star of similar size and type to the Sun approximately 12 light-years away, also hosts a planetary system and is a target of interest for astrobiology. Epsilon Eridani, about 10 light-years away, is a young star similar to what the Sun was several billion years ago, surrounded by a disk of debris that may be in the process of forming planets. The stellar neighborhood within a few dozen light-years of the Sun is rich with stars at different evolutionary stages, each with its own potential for hosting worlds and life. When the Sun dies in 5 billion years, most of these nearby stars will still be alive. The red dwarfs will be far from their end. Some Sun-like stars will have already completed their own journeys through the red giant phase. The neighborhood will look very different from what it does today, but it will not be empty. The galaxy will continue its quiet work of shining and evolving, as it has done for 13 billion years before the Sun was born. The sun has served as humanity's master clock throughout history. Before mechanical clocks, before digital time, before atomic precision, the sun's movement across the sky was the most fundamental measure of time available to any human civilization. The day is defined by one rotation of Earth relative to the sun. The year is defined by one revolution of Earth around the sun. The seasons are defined by the angle at which sunlight strikes Earth's surface as Earth orbits. The entire agricultural calendar that made civilization possible, the planting times, the harvest times, the festival calendars of every ancient culture, all derive ultimately from the movement of the sun. The sun's reliability as a clock is almost perfect. Its apparent motion across the sky is so regular that civilizations that watched it carefully could predict eclipses, solstices, and equinoxes centuries in advance. The Maya, the Babylonians, the ancient Egyptians, the builders of Stonehenge, all developed astronomical knowledge sophisticated enough to track the sun's yearly cycle with precision that modern measurements confirm was genuinely accurate. The Earth's orbit is not perfectly circular, and the tilt of Earth's axis creates the variation in day length across the year, but these effects are regular and predictable. The variations in the sun's apparent position from day to day follow mathematical patterns that ancient astronomers discovered empirically and that modern physics can derive from first principles. As the sun ages and its luminosity gradually increases, the length of the day, the year, and the seasons will not change significantly. Those are determined by Earth's rotation rate and orbital mechanics, not by the sun's luminosity. What will change is the quality of the light, the amount of heat, the effects on climate. But the sun will continue to be a reliable timekeeper even as it slowly becomes a more dangerous one. The precision with which the sun can serve as a clock is now exceeded by atomic clocks that measure time based on atomic transitions rather than astronomical motions. The second is now defined not as a fraction of the solar day, but as a specific number of oscillations of cesium atoms. But the fundamental human experience of time, the rhythm of days and years, the sense of morning and evening, is still organized by the sun's apparent motion. When the sun becomes a red giant and Earth's surface is scorched beyond habitability, whatever continues in the outer solar system will orbit in cycles that are no longer measured in familiar days and years. The timescales of that future solar system will be alien to any experience rooted in Earth's current relationship to its star. The clock that has ticked for 4 billion years will have changed beyond recognition. This journey has taken us through 4.6 billion years of the sun's past, through 5 billion years of its future, through the physics of nuclear fusion and stellar evolution and planetary fates and galactic mergers. It has taken us to the edge of what the sun's story can tell us about the universe and about ourselves. What remains after all of that is what was always there, the sun doing what it does. In a few hours, the Earth's rotation will bring this part of the surface back toward the sun. The first photons of morning will reach the horizon, scattering through the atmosphere to produce the colors of dawn. The temperature will begin to rise. The birds, if it is a season for birds, will register the increasing light. The photosynthetic organisms of the world will begin capturing energy and building molecules. The day will begin, as it always begins, with the return of the light. That sunrise is not the same as any sunrise that has come before, in the sense that no moment repeats. But it is continuous with every sunrise that has come before, all the way back to the first sunrise witnessed by the first organisms with anything resembling photoreception, billions of years ago in an ocean we can barely imagine. That long chain of daily beginnings, every dawn since the beginning of life on Earth, all the way to this particular morning in this particular place in this particular moment of history, is one of the most remarkable continuous threads in the known universe. Tomorrow's sunrise is part of that thread. And so are you as you witness it. The sun will keep shining. 5 billion years from now it will begin to change. But that is so far away that it is, for any practical purpose of living and experiencing and being present in the world, completely beyond the horizon of relevance. What is not beyond any horizon is tomorrow morning. The photons are already on their way. There is an experiment you can do at any moment that produces a kind of wonder that almost nothing else can match. Stop what you are doing. Find sunlight, direct or indirect. Feel the warmth on your skin. That warmth is nuclear fusion, 400 million kilometers away, arriving in the form of infrared photons after an 8-minute journey through empty space. Those photons were generated in the solar core between 100,000 and 1,000,000 years ago. They bounced through the dense solar interior for that enormous time, losing energy with each absorption and re-emission, shifting from gamma rays to X-rays to ultraviolet to visible to infrared. They escaped the solar surface, crossed the vacuum of space, entered Earth's atmosphere, penetrated whatever was between the atmosphere and your skin, and were absorbed by the molecules of your body, converting their energy to heat. All of that in the moment that you feel warm in the sun. The warmth you feel is not new. The energy arrived at this planet long before the first multicellular animals existed. The same energy that warms you has been warming this planet for 4 billion years, sustaining the processes that made complex life possible, that drove the evolution of every species that has ever existed, that powered the civilizations that built the world you live in. That particular packet of energy, those specific photons, have been on their journey since before the beginning of recorded human history. And now they have arrived, and their journey has ended in the warmth you feel. It is an ordinary miracle, one that happens billions of times per second on the sunlit side of this planet. So ordinary that it goes unnoticed. So fundamental that its absence would be immediately noticed, and would be fatal within hours. The sun's death, billions of years away, will be the end of that warmth for this world. But that ending is so distant that it cannot be experienced as loss in any present tense. What can be experienced is the warmth itself, present and available and asking only to be noticed. Tonight the warmth is absent, turned away by the planet's rotation. Tomorrow it will return, as it always does, as it has done for 4.6 billion years, as it will do for 5 billion more. In that pattern, in that reliability, there is something that no human institution has matched and no human achievement has equaled. A consistent source of warmth and light that has not failed in 4.5 billion years, that will not fail tomorrow, and that will not fail for a time so long it is beyond any meaningful comprehension. This is a long story, told tonight in the space between waking and sleep, in the particular quiet that comes when the day's demands have receded and the mind can rest with something larger than itself. The sun story is not a sad story. A life of 10 billion years, spent producing the conditions for planets and life and chemistry and consciousness, ending in a beautiful display of glowing gas and then a long quiet rest as a cooling compact object, is not tragic. It is simply what stars do. And what stars do has produced you. The nuclear fusion in the sun has been generating the energy that flows through every living thing on Earth for 4 billion years. Every meal you have eaten, every movement you have made, every thought you have had, is powered ultimately by sunlight either directly or through the food chain that begins with photosynthesis. You are, in a literal physical sense, sunlight that has learned to think. That may be the most extraordinary sentence that physics makes possible. A process that began with nuclear fusion in a star's core, that produced photons which traveled for hundreds of thousands of years through the solar interior, that escaped and crossed space to a small planet, that were captured by molecular machines and converted to chemical energy, that drove metabolic processes over billions of years of evolution, has produced, in one of its most recent configurations, something capable of understanding what it is and where it came from. The sun does not know any of this. It is a vast ball of plasma governed by the laws of physics, producing energy and sending it outward in all directions, indifferent to whether any of it is captured by life. But from within the perspective of the life that has captured it, The sun is the source, the original source, the reason for the warmth, the light, the food, the energy, the possibility of existing at all on this particular planet in this particular moment. That is worth knowing before sleep. That is worth carrying into the dark. The sun is shining on the other side of the world. Tomorrow it will return. It always does. Modern solar astronomers have tools that transform the experience of observing the sun from seeing a bright disk in the sky to reading the physics of a nuclear furnace in real time. The Solar Dynamics Observatory, launched in 2010, observes the sun continuously in multiple wavelengths of ultraviolet light invisible to human eyes. In those wavelengths, the sun looks nothing like the serene yellow disk familiar from casual observation. It is a roiling, dynamic, magnetically active object with plasma loops arching hundreds of thousands of kilometers above the surface, bright active regions where the magnetic field is most intense, and dark coronal holes where the solar wind escapes most freely into space. The images the SDO returns every 12 seconds, 24 hours a day, have produced a catalog of solar activity more complete than anything previously possible. Researchers can watch solar flares evolve over minutes, track the growth and decay of sunspot groups over weeks, observe the sun's differential rotation, with the equator rotating faster than the poles, create the tangled magnetic fields that drive the activity cycle. The Parker Solar Probe, launched in 2018, is making the most ambitious observations yet by approaching the sun far more closely than any previous spacecraft. At its closest approach, it comes within about 6 million kilometers of the solar surface, inside the corona, the region where the solar wind originates and accelerates. The data it is returning is helping answer fundamental questions about why the corona is so hot and how the solar wind achieves its tremendous speeds. What astronomers see when they look at the sun with these tools is a star far more complex and dynamic than the stable light source it appears to the naked eye. It is a living system with cycles and storms and eruptions and flows, operating according to physics that we understand in outline but still not in every detail. That complexity will continue throughout the sun's remaining 5 billion years on the main sequence. The solar cycle will continue. Flares will erupt. Sunspots will come and go. The corona will maintain its mysterious excess heat through mechanisms still not fully understood. The sun will be, in all those respects, the same kind of active and complex object it is today, only gradually, imperceptibly brighter as the eons pass. Understanding that activity, that complexity, that dynamic character, is part of what makes the sun not just a light in the sky, but a genuinely fascinating object in its own right, worthy of the thousands of scientists who have dedicated their careers to studying it and the billions of dollars in instruments humanity has invested in watching it. The sun will rise tomorrow. You may or may not be awake to see it, but it will happen, as it has happened every morning for 4.6 billion years, as it will happen every morning for approximately 5 billion more. In that specific, simple, reliable fact, there is something worth holding. Not as philosophy or wisdom or consolation, just as a fact about the world we live in that is easy to take for granted and extraordinary when actually considered. 4.6 billion years of sunrises. Every morning on Earth that has ever been, going back to a time when there was no land above the water, when the oceans were young and the atmosphere was nothing like what we breathe, when the only life was microscopic and chemical. Every morning since, through the development of complex cells, through the explosion of multicellular life in the Cambrian, through the age of dinosaurs, through the emergence of mammals, through the evolution of primates, through the rise and fall of every human civilization, through this particular night and toward this particular dawn. 5 billion years of sunrises still to come. Through changes in climate and biology and geology that we cannot predict. Through the slow warming that will eventually make Earth uninhabitable. Through whatever comes after on the surviving outer worlds. Through the red giant phase and the planetary nebula. all the way to the cold white dwarf drifting in the darkness of a future universe. There is one more thing worth saying, a thing that requires no elaboration because it is its own elaboration. Every atom that has ever been part of your body has been part of the sun. Not this sun, but the generation of star that preceded it. The material of the solar system, before it was a solar system, was the dispersed remains of at least one previous stellar generation. The atoms that today are in your blood, your bones, your brain, were processed through the nuclear fire of a star that lived and died before the sun was born. And when the sun dies and expels its outer layers, those atoms will be on the move again. Some will be incorporated into the white dwarf. Many will disperse into space. And eventually, in the vast cycles of galactic time, they will find their way into something new. You are not just the product of the sun. You are a temporary configuration of atoms that have been through stellar fires before and will go through more. The sun is your current host, the energy source for the specific chapter of your atom's journey that has produced you. But the journey is longer than the sun, longer than Earth, longer than the life forms that have inhabited it. That is the deepest context available for thinking about who and what you are. Not just a human being in a historical moment on a particular planet, but a temporary arrangement of matter with a history reaching back to the beginning of the universe and a future extending beyond any horizon you can see. 8 minutes. That is how long it takes sunlight to travel from the sun's surface to Earth. 300,000 kilometers per second, multiplied by 480 seconds, equals 144 million kilometers, very close to Earth's average distance from the sun. In that 8 minutes, the photon that left the sun at the speed of light while you were reading the sentence will have already reached you if you are reading slowly enough. It crossed the inner solar system, passing the orbit of Venus, reaching Earth's orbit, entering the atmosphere, scattering off molecules and particles, and arriving somewhere on the sunlit side of the planet. 8 minutes is not very long by human standards. It is roughly the time of a short shower or a brisk walk to a nearby destination. And yet in that 8 minutes, light crosses a distance equivalent to traveling around Earth's equator almost 4,000 times. That ratio, the inconceivable speed of light measured against the comprehensible scale of human time and distance, is one of the most mind-bending aspects of astronomy. We describe distances in light years not because astronomers are being poetic, but because light years are practical units for the distances involved. The nearest star beyond the sun is 4 light years away. Light from that star takes 4 years to reach us. If that star flickered tonight, we would not know for 4 years. The sun is 8 light minutes away. We live in what is effectively real time with our nearest star. 8 minutes is close enough that solar storms can affect Earth within hours of their origin. It is far enough that the sun's own light takes 8 minutes to make the journey. That 8-minute window is the most intimate astronomical relationship Earth has. No other star is within a month of light travel time. No other astronomical object produces measurable warmth on Earth's surface. No other astronomical object determines the daily and seasonal rhythm of life. 8 minutes. That is the distance, measured in light, between you and the thing that makes your existence possible. This has been a long journey through time, from the sun's origin to its death, from the present moment of its life to the far future of the universe. We have covered physics and chemistry and geology and biology and philosophy, all in the service of understanding one thing. What is the sun, and what will become of it? The answer, condensed to its essentials, is this. The sun is a star, one of 400 billion in the Milky Way, currently in the middle of its main sequence life, converting hydrogen to helium in its core at a rate of 4 million tons per second. It formed 4.6 billion years ago from a collapsing cloud of interstellar gas. It will continue on its current path for approximately 5 billion more years, gradually brightening as its core composition changes. Then it will expand into a red giant, eject its outer layers as a planetary nebula, and leave behind a white dwarf that will cool slowly over trillions of years into cold darkness. That is the story. It is a long story, told by physics, verified by observation of thousands of other stars at different stages of the same journey, consistent with everything we know about how matter and energy behave in the universe. And within that story, right now, we are in the sun's comfortable middle age. The hydrogen is still abundant. The balance between gravity and pressure is stable. The light and heat are reliable. The conditions enabling life on Earth are present. They will not be present forever, but they are present now. One last thought, very simple, before this night ends. A photon left the solar core between 100,000 and 1,000,000 years ago. It bounced through the dense solar interior for all of that time, being absorbed and re-emitted countless times by the particles it encountered, moving slowly outward despite its speed because every step forward was followed by many steps sideways. It reached the photosphere, the sun's visible surface, and escaped. It crossed 150 million kilometers of vacuum in 8 minutes. It entered Earth's atmosphere. It scattered off molecules, reached the surface, perhaps warmed the ground, perhaps fed a plant, perhaps traveled through window glass into a room where someone lay awake in the dark thinking about the sun. And then it was absorbed. Its journey ended. Its energy converted to heat in the molecules of whatever received it. The photon ceased to exist as a photon. Its energy continued, in the warmth it produced, in the chemistry it drove, in the life it sustained. That is what the sun does. Continuously, for 4.6 billion years. Sending out photons on journeys of 8 minutes, powering the world from 150 million kilometers away, converting its own mass into the light and heat that make this planet possible. The night is quiet. The sun is on the other side of the planet, doing what it always does. The stars that are visible, if you could see them now, are other suns at different stages of their lives, each one burning, each one following the same physics, each one part of the same story at a different chapter. The universe is large. The sun is one star among 400 billion in this galaxy alone. And yet it is the one that matters to life on Earth in the most immediate way possible. Not the most massive, not the brightest, not the most dramatic. Just the closest. Just the one with the right kind of planets in the right kind of orbits, producing the right kind of light at the right intensity. In all that vast dark, the sun is a warmth within reach. A warmth that tomorrow morning will return, as it has returned every morning for 4.6 billion years, as it will return every morning for 5 billion more. Tomorrow the sun will rise at its appointed time, determined by Earth's rotation and your latitude on the planet. It will clear the horizon and the sky will brighten, and the day will begin with the same simple fact it has begun with for 4 billion years of life on Earth. There is light, there is warmth, there is energy for living. The sun of tomorrow is not guaranteed in some cosmic sense. Stars can be disrupted by nearby objects, though nothing near enough to affect our sun is on any collision course. Solar activity can intensify, though the sun is currently in a period of moderate activity with no unusual events anticipated. But for any practical purpose of daily life, tomorrow's sunrise is one of the most certain events in the future. That certainty is itself extraordinary. In an uncertain world, the sun's reliability is absolute on any time scale relevant to human experience. It was rising when the first hominids walked upright. It was rising when the first cities were built. It will be rising long after the last human being who is alive tonight has died. It will be rising for 5 billion years after the last member of our species, however our species transforms through evolution in that time, has disappeared. 5 billion years of sunrises still to come. Tomorrow's is one of them. If this journey kept you company tonight, subscribe to the channel. There are many more worlds waiting to be explored in the dark.